Hello students, welcome back. We are on the way of studying one of the important segments of electrostats, that is Gauss Theorem and its applications. We will be covering three important applications of Gauss Theorem. Today we will be dealing with the first application, that is to find the electric field due to thin, straight, uniformly charged, infinitely long wire. The thing is that whenever we are studying something and we say it is important, one question strikes us, why? Why is it important? हम क्यों पढ़ रहे हैं Gauss Theorem? Obviously वो आपके syllabus में है और important है इसलिए पढ़ रहे हैं, लेकिन इससे भी ज़्यादा the main thing you need to understand is Gauss Theorem का real life application क्या है? हम इसे कैसे अपने real life में या इसके further practical applications क्या हैं? The important thing is about Gauss theorem is it is universal law of nature. ये एक universal law है and universal law is something which can be applied, like Gauss theorem can be applied to almost every type of field where inverse square law relationship is obeyed in space. Second thing, it solves some of the complex problems of electrostats by simplifying the situation by applying symmetries like cylindrical, spherical or planar symmetries. And above all these things, it finds application in acoustic, sound acoustics also. It can be used to find distribution of sound intensity in space. So these are some real life applications which keeps Gauss theorem something which needs importance and which has to be studied with quite good concentration. Today we will start with the first application. First application is to find electric field due to thin. Understand the characteristics of the wire, charged wire. It is thin, straight, uniformly charged with charge density lambda, infinitely long wire. Now the thing is that whenever we use this word infinite, what do we mean? Infinitely long wire doesn't mean that its length extends from earth to moon. Infinitely long wire means the wire whose length is much greater than its own radius. Means it's very thin. Radius is very small, length is quite large, so when compared to radius, length is large, you call it infinitely long wire. Can you see the situation? This is a charged wire, infinitely long. For convenience, we have taken it positively charged. You can have it even negatively charged also. Now, the length of the wire is L. The charge density, charge per unit length is lambda. What is P? As usual, it is our observation point. Means it is the point at which we are interested in finding the electric field. What is R? This is the distance of the center of the wire from the observation point. Can you see it here also? Same wire of length L having observation point P at a distance R from the center of the wire, uniformly charged. Now how to find the electric field? What is lambda? Lambda is the charge per unit length. You call it uniformly charged and this is called charge density. Charge per unit length. Now how to find the electric field? The thing is we have to find the electric field. So you know what is the first step in applying Gauss theorem? Correct. We have to choose a Gaussian surface. So the question is, what should be the suitable Gaussian surface chosen so that we can conveniently apply Gauss theorem here? So let's look what can be the suitable Gaussian surface here. So how to find the electric field? We decided we have to choose a proper Gaussian surface. Here in this situation, for symmetry, what have we chosen? We have chosen a cylinder as a Gaussian surface. What are the criteria? The cylinder which we have chosen, it is having the same length L as the length of the wire itself. The radius of the cylinder is R, the distance of the observation point from the wire, and the line charge as axis. The cylinder which we have chosen is having the line charge as the axis, R as the radius, and the length of the cylinder is L, that you can see in the diagram itself. And moreover, we are having S1 and S2. These are the top and bottom closed ends of the cylinder, and S3 is the curved surface area of the cylinder. S1 and S2 top and bottom, and S3 is the curved surface area of the cylinder. Now what will be the direction of electric field? Obviously the line charge is positive, therefore we are expecting the electric field at all points to be radially outwards. It will be radially outwards if it is a positively charged wire, and if it is a negatively charged wire, then it will be radially inwards. So I hope you got the Gaussian surface. Now let us see the mathematical expression. The Gaussian surface we have chosen, now it can be subdivided into three different parts. Surface S1, as I told you, and S2, the top and bottom closed ends. S3 is the closed surface area. Out of this S1, we have chosen a small part, ds1, the area vector, and it's always outward normal, you know it. And the electric field, as we told you, that it will be radially outwards at all points. So at this particular point, the electric field is radially outwards, and the area vector, small area out of S1 we have chosen, is outward normal ds1. The angle between ds and electric field is 90 degrees. Why we are finding it? Because we know flux phi is E dot ds. We know that phi is equal to integral E dot ds. We have to know the angle between electric field and the area vector. Let us see the second bottom end. Here also the area vector is outward normal ds2, and the electric field as usual is radially outwards. The angle between area vector and electric field is 90 degrees. They both are perpendicular to each other. So the flux contributed in these two closed ends will be zero. The component of electric field along these two closed ends will be zero. The flux contribution will be zero because electric field is perpendicular to the area vectors. And the third curved surface area. Here I have chosen a small part from the curved surface area ds3. Out of S3, we have chosen small part ds3. This ds3 is having an area vector outward normal along this direction indicated with the arrow ds3, and the electric field is as usual radially outwards. So what is the angle between E and ds3? The angle is 0, means electric field and the area vector, they both are in same direction. And in this particular section, you see that there will be contribution for the flux. You can refer to these diagrams also. These diagrams are also representing the same things with different perspectives. One is giving you the horizontal view of the same line charge, where we have taken the line charge in a horizontal section, and the other one is giving you the vertical look of the same situation, and they are still conveying the same message. If you have had enough look at the diagrams, shall we write the mathematical expressions? So we have established that the electric flux is only through curved surface of cylinder. It is the curved surface of the cylinder which is contributing to flux. Rest of the two bottom and end surfaces, the top and bottom surfaces, they are not contributing to the flux because ds and E are perpendicular to each other. Electric flux is only through the curved surface. Writing the mathematical expression. This is something we know. Flux, total flux is equal to closed integral of E dot ds, which is again equal to Q by epsilon naught according to Gauss theorem, and Q itself is product of lambda into length of the particular wire. So it is Q equal to lambda. We have written this expression now. Total flux E dot ds can be written as flux through first surface S1. This is the first surface S1, E dot ds1, plus flux through second surface S2, E dot ds2, plus flux through third surface S3, which is E dot ds3. Sum total of all these three will give us total flux. So moving again. So we got the conclusion that total flux phi, which is closed integral of E dot ds, is equal to 0 for the first surface ds1, where the angle between electric field and ds1 is 90 degrees. So E ds cos 90 is 0 plus the third surface, it is S3, which is E and ds are in same direction. E ds cos 0 results to 1. This is same direction. Then the second surface, for the second surface, the bottom surface, the angle between E and ds is again 90 degrees, so the flux is 0. So we get 0, 0, and only for the third surface we get, that is the curved surface, E ds cos 0. So we are getting phi E ds is equal to only this term, and E ds cos 0 is nothing but E ds integration over S3, and this term we can write it here directly. We will take electric field E out of the integral because E is constant over the entire surface. So we take it out of the integral. S3 integration of ds3. We can write it here or we can write it here also. So what is ds3? It is the curved surface area of cylinder. What is ds3? This integration is curved surface area of the cylinder. So what is the result you are getting here? E is outside the integration. ds3 for the curved surface area of the cylinder, it is 2 pi r radius into L. E into 2 pi RL. This is equal to phi, and phi is equal to lambda L upon epsilon naught. We have already seen it in the previous steps. So simplifying, what will we get? We'll get it from here. I'm cleaning these steps. What am I getting here? Phi is equal to E into 2 pi RL is equal to lambda L upon epsilon naught. This is something we are getting here. Simplifying, L gets cancelled. What am I supposed to find out? Yes, we have to find out the electric field. E is equal to, take the other steps on the other side, 1 by 2 pi epsilon naught multiply by lambda upon R. This is the value we are getting for electric field. If I have to write the electric field in vector relation, if I am to write it in vector relation, I'll get E is equal to, we can write it as 1 by 2 pi epsilon naught lambda upon R in the direction of R cap. This is the electric field vector, which is 1 by 2 pi epsilon naught lambda upon R, that is the surface line charge density upon R into R cap. The direction is along R cap. So what have we concluded here? Here electric field is proportional to 1 by R. This is something of prime importance. We need to understand E is proportional to 1 by R. Whereas for a point charge, E is proportional to 1 by R square. For a dipole, short dipole, it is E is proportional to 1 by R cube. But for a line charge, E is proportional to 1 by R. So this is the conclusion we are getting for the vector relationship of electric field. So we are getting this relationship, and you can refer to the diagram also, which is supporting the mathematical steps. So we are through with the mathematical steps of finding electric field at any point P at a distance R from the line charge using Gauss Theorem. And we arrived at the conclusion that the electric field is 1 by 2 pi epsilon naught lambda upon R into R cap. The direction is radially outwards. If suppose the line charge is negatively charged, if the entire line charge is having negative charge, then the electric flux will be radially inward in direction, but rest of the steps will remain the same. Only there will be a change in the direction of electric field. And if the line charge is positively charged, then we have seen it is radially outwards. This particular expression comes out to be accurately true, especially for the midpoints of the wire where we neglect the end effects. Otherwise, this is more or less what you can say an application of Gauss theorem to find electric field, and you get a conclusion E is inversely proportional to R. This is one of the important conclusion, and you try to plot a graph, else we'll do it in the next episode. Stay connected, stay tuned in. We will be looking into other applications of Gauss theorem. Hope you are enjoying. Thank you. Goodbye.